All right.
Woot.
We did it. We're live, I think. As
Yay.
always, we need somebody to tell us.
We dance. Dancing.
It's just like the, hold on, that way, and then I can look that way. Yeah.
I don't know who you're looking at, but that's okay.
Well, you're down that way, and Moya's that way.
Over there,
and
so
Dave is there.
Just need motion to know the video's not frozen. So.
Yeah.
Thank you for indulging me, Moya.
Always.
Yeah, crazy week. What a week. What a great week. Like, for all kinds of interesting things, which we're about to get into shortly as well. But we got a ton of space exploration news. We've got a ton of astronomy news. So I think we're going to have a lot of good stuff to talk about. We've got a special guest, but that's going to happen at the end of the show. So stay tuned for that. How long is the interview? 20 minutes, 19 minutes and 24 seconds. So we will run the interview around the 40-minute mark. All right, you've all had a chance to say hello, so I'm going to say hello back. Or will I?
One last chance to get your name in the list.
Yeah, come on, YouTube.
Go say hello in the chat.
Hello to Fifth Dimension, Bob Moeller, Brandon Whedon, Christian Woodland, David Dunn, David Fairweather, JN88, Jorn Albert, Larry King, Miss Brick Kitten, Nancy Graziano, Nifty, Rich Wilson, Arjone, Robert Shaw, Scott Bragdon, Tom Van Scotter, and Zaffen. Hey, everybody. David Dunn is asking, did she get her PhD? Yes! Oh, man, spoiler alert. Yes, she got her PhD. We'll talk about that in the actual show.
You should change your name on the little label.
The doctor, yeah. Really rub it in people's faces, yeah.
Celebrate. It's not rubbing it in faces. It's celebrating.
Yeah, I guess there's like a line. You celebrate for a while, and then all of us
you got it with the exclamation point.
Yeah.
So people know I'm excited.
There we go. PhD. Yeah, nice, with the exclamation mark. Yeah, that's right. That's the celebratory version. If you put the Esquire after, then it's... okay.
And that's bragging a little bit.
There's a fine line.
Yeah. All right. I'm going to put you guys all back in your boxes.
Sorry to all the Esquires out there.
I don't even know what that means. What does it mean if you're Esquire?
British, is it?
Is that what it means?
I always thought it had something to do with being a lawyer.
I thought so too.
I think so, yeah. That
okay.
Right.
Someone educate us in the chat, would you?
Yeah, that'd be great. All right. Back to me. Here we go. Welcome to the Weekly Space Hangout for Wednesday, April 21st, 2021. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, finally, the Mars helicopter flies. An exoplanet where an exoplanet shouldn't be. Scientists baking meteorites to investigate the atmospheres of alien planets. Of course, we're going to be talking about the upcoming space flight and the giant contract awarded to SpaceX to land humans on the moon. All right. First, let's see. On my screen, I've got Dr. Kimberly Cartier. Kimberly.
Hello, Fraser. Happy podcast day.
We got Dave Dickinson. Dave.
Hey, I've sent the giant binocs back, and I'm down to a monocular now telescope once again. So
But that's your telescope, right?
That's my travel scope. Yeah, that's my typical little 5-inch Maksudov Cassegrain scope that I.
It's not your travel tripod, though, right?
No, I can travel with that. You have to check it. It doesn't quite go in a carry-on, but the tripod breaks down pretty small.
But
so
it looks like it's about 50 pounds.
That scope almost got confiscated in Morocco. True story.
Wow. It's surprising that you took it. All right. And last but not least, we've got Dr. Moya Mcteer. Moya.
Hello.
Congratulations.
Hi, thank you.
Yeah, congratulations.
Tell us the story. What happened?
I gave a defense about 2 weeks ago. I gave a public talk about my research. I was grilled about it for 2.5 hours by my committee. And then they sent me into a Zoom breakout room because that's how things happen these days. And then I got a PhD and it was exciting.
That's awesome. And we were talking about this before the show that you live streamed a big chunk of the whole event. So not only were you experiencing this all through Zoom, but anybody who wanted to could actually see what a PhD defense looks like and follow along and cheer you on. And you had a lot of people watching. It was a pretty big event.
Yeah, I'm very lucky to have people supporting me in that. It's on YouTube, and the link is horrendous, but if you go to my Twitter page, it's in the pinned tweet if you want to watch the YouTube defense talk. I've tried to make it so that anyone can understand at least parts of it.
And do you think, was that a good idea, do you think, to do that? Are you glad you did?
I'm really glad I did. I think it was especially important for me because I'm not staying in academia and I'm going into science communication full time. So this is a good way to enter that stage of my life, but it might not be the best choice for every single PhD defense out there.
Science communication full time. That sounds familiar to everybody else who's in this show today. So yeah,
I approve of this life choice.
Yeah, me too.
For no reason whatsoever.
Right. You're not biased at
randomly,
all.
Not biased. No, of course.
Yeah,
of course not.
No, absolutely. Can concur. Science communication is a great job. All right, let's before we get on with this week's news stories, I want to give a big shout out, of course, to our good friends at the Weekly Space Hangout crew. They're our friends, our fans, our executive producers. They organize the guests. They help with just keeping all of the cats herded. Apparently I have to say those words very carefully because people think that I'm herding cats as opposed to herding cats. But yeah, so big thanks. If you want to join this amazing community, go to wshcrew.space. They will give you everything you need to be able to join this amazing community and join us every week. All right, let's get on with this week's story. And Dave, we got to talk about the helicopter.
Yes, Mars Ingenuity, NASA's helicopter on Mars, finally did its very, very short flight, but the first flight on another planet Monday. There was a little bit of drama last week when originally it was going to go last week on this time, last Wednesday. And then when they did the spin-up test, it shut down prematurely. And they had to troubleshoot it and upload a new program to it. And that necessitated bumping the flight back to Monday morning. But it did its flight, went up 3 meters, hovered 30 seconds, which was a little longer than the Wright brothers' 12-second flight. And they named the flight, they had the connection. They named the launch site Wright Brothers Field in honor of it. And there's a little bit of the Wright flyer, about postage size stamp, that's affixed onto Ingenuity. And I just saw on Twitter, NASA JPL sent out that tomorrow morning they're indeed doing the second flight.
Already?
So yes, that was the idea anyway. April 22nd was right about, we heard that the second one. This one's going to go up to about, they want to go up to about 50-second flight, 5 meters height, about 15 feet. And they want to try to do a little bit of a lateral flight. So they're going to go up. They're doing everything incrementally, of course. So they're going to go up. They're going to fly a little bit to the side. Then they're going to come back down. And this is just a proof of concept. There's really no science on this other than there's 2 cameras. There's a high res. The first camera you see, there's a black and white 0.5 megapixel camera on it. Those are the low data rate cameras that you see that came back immediately where the helicopter saw its shadow. And those images we got back first. Later in the day, we actually saw a GIF of the helicopter going up and coming back down, and that was about the height of the excitement for Monday. So it's so it's in a way it's they're taking things very slow. They're doing 5 flights over the span of 30 days. They've got a 30-day window to do this, and they've got about 2 weeks left on it, what they said on the press conference. So they're going to start doing more challenging flights as they get going. Like I said, they're going to try to fly up and fly lateral tomorrow. Then they're going to fly out maybe 50 meters on the 3rd flight. And I haven't heard on 4th and 5th what they're going to do, probably higher, longer, further flights, and try to image. Perseverance, of course, is backed off a ways, and it's watching all this and documenting it. That's where we got the actual video GIF of the helicopter going up and coming back down. But it's a first. So, and of course, NASA wants to do more challenging helicopters like Dragonfly on Titan launching in around the 2027 timeframe. Now, this is going to be a big nuclear powered helicopter, so it's naturally going to be, Titan's going to actually be a little easier to fly in because the atmosphere is much thicker than Mars. So you've got that going for you.
Less gravity, thicker atmosphere than Earth.
Mars has less gravity than Earth too, but it also has a very, very tenuous atmosphere. That's why this little tiny box-sized rover has these 4-foot-long blades to try to, it's got to get all the gravity it can against Mars's very tenuous atmosphere.
Hal McKinney is asking, how do they secure the helicopter when it's not flying?
It's just sitting there on the surface. I mean, it's not, and there's no way for Perseverance to, if it tips over when it lands, it's basically done. There's no way to upright it, or there's no way.
I'm sure they'll try.
I would think it'd be cool eventually to have one that would fly back to a base station on the rover, fly back, sit there, park, charge, go along with it. Because ultimately what these could be doing is scouting terrain. These could be going up ahead, flying, mapping the terrain, kind of coming back to the rover. If there was things like cliff faces where the rover couldn't get up to, something like a little helicopter could do that. So ultimately, there could be some real science done with something like this.
I mean, it's important to note that the air pressure on Mars is so low that there could be a hurricane flying through the site, hurricane force or speed winds, and it wouldn't knock the helicopter over. You could not fly a kite in a hurricane on Mars.
It's like 1%.
Yeah.
That's what Andy Weir said famously, and a lot of people pointed out about The Martian, about the whole premise of he's like, I had to have some premise to kick off the whole story, but the whole thing of the dust storm on Mars, like wiping everything out, probably wouldn't really have occurred like that. But I've seen that in a lot of science fiction. Mars stories seem to always have a dust storm in them somewhere. So,
and Lionel L is saying in the chat that Percy was doing MOXIE stuff. So the MOXIE is the oxygen experiment on board Perseverance. Do you want to talk about that?
Yeah, that they're doing that just to show that in situ that they could actually generate oxygen on Mars with this. Again, another little proof of concept mission, but eventually when there's crewed missions going to Mars, hopefully in the next decade, I hope so, because I'm getting old. I'd like to see like actual crewed missions get to Mars in the 2030s.
Right.
So it'd be handy if they could do some living off the land, as far as getting energy and oxygen and things like that.
So I heard an estimate. It was 10 minutes of astronaut oxygen is what they were able to produce. So it would keep an astronaut alive. Now, Kimberly, you had been sitting on this story, I think a couple of weeks ago, right, about a helicopter on Mars. So finally it flew. Where were you when the helicopter flew?
I mean, it was like 6 a.m. on the East Coast when it flew, so I was definitely asleep.
Yeah, it was 3 a.m. for me.
I woke up and I logged into my computer for work at 8, and I was like, I missed it.
So I told my wife.
How did I miss it?
I
watched it over and over again afterwards. But yeah, that's where I was.
I was tasked to write about it for Sky and Telescope, and I told the wife, it's like they had to fly it right on Monday morning. So it's like probably the worst time news cycle-wise. But
they announced it like on Sunday, and I was.
We kind of knew, unless something unexpected happened, that really ultimately we're going to see a GIF at the end of the day of the helicopter going up and coming back down. That's going to be the extent of the story.
I was like super excited when the original one was going to be like in the middle of my workday. I was at my computer. I was ready to live tweet it. It was great. And then nothing. And then, of course, they went like the one time when I'm definitely not paying attention, because they should have planned it around my schedule.
Yes.
Not like the conditions on Mars and the readiness of the helicopter.
Yeah, they should they should be like, are you done? Have you got time now? Kimberly, can we fly now? Can we?
You good?
Can we light this? Can we fly this now? Yeah.
I want to refresh my coffee first.
Yeah. Well, so for me, I was, 3 a.m. I was completely asleep, and so I had to wake up.
Yeah. Where were you?
Well, of course, the first thing I did when I get up is
not being there. Where were you?
I checked Twitter, and I get up early. I get up at like 5:30. I check Twitter at like 5:30 in the morning. I'm like, okay, I guess it's time to go to work.
I pretty much drafted up the story, and I knew there was going to be a press conference too that afternoon. Like I said, it was one of those stories. It's like, I can probably write 90% of this before, and then you'll get the quotes from the press conference, and then there'll be the photos, and you just put those. It's like, I can probably have it 90% done before the press conference, because unless, like I said, it tipped over or did something unexpected, that there's the extent of the story is it flew, it went up and it came down, and here's how long it flew.
Yeah. It was a long press conference too. They really showboated, I think, after that. They spent a long time, and they had a lot of great information about it, but still it was
they gave a little more preview on the next flights. That's where a lot of that information came out of. That was probably the most important thing I got out of it. It's a preview for the next flights.
Awesome. Well, it's fantastic. I'm sure we're going to be just reporting, having very similar echoes of this conversation for weeks in advance. I love this idea of one of these flying with every future rover mission that goes to Mars, every lander, whatever, to just do some, as you say, scouting around. I mean, if they do sort this out, I mean, it'll be invaluable for
Dragonfly is going to be very interesting. I'm interested to see that take shape. So I'm glad they selected that. It's going to be a very cool mission.
Yeah, no, total surprise that it flew or that joined the mission. And it sort of feels like a bit of a dream that this crazy idea went on board this awesome rover, went to Mars, and now has flown. So yeah, it's good. It's a very good week. I'm really excited. All right. Kimberly, what have you got for us?
I have an exoplanet that is somewhere that it shouldn't be, and we don't know why it's there. So that's the entirety of the story. No, I have details. It's not just any old exoplanet. It is an exoplanet called YSES-2b. It's an exoplanet mission I've not heard of before, but it's a direct imaging mission that's focused on a very specific star group called the, where did I write it? The Lower Centaurus Crux subgroup. It's part of the Scorpius-Centaurus Association. It's a pretty well-studied area of the sky, and they're looking using direct imaging for planets around these very young stars. The stars themselves are only about 14 million years old. And so they're about the right age for us to go look for directly imaged planets, because the planets themselves will also be very young, which means that they'll still be nice and hot and glow in the infrared, which is just what you need for direct imaging. So as part of this mission, looking at this young star group, the team found an exoplanet, which is great. We always love when that happens. However frequently that it does happen, we love it every time. This planet was very, very, very far away from its star.
How far? I'll bite. How far was it?
Is it?
Yeah.
110 light years away.
110.
Which is,
do you mean astronomical units?
Sorry, astronomical units. Sorry, astronomical units.
Yeah.
Blah blah blah. I'm mixing up units. Sorry.
Ph.D. please.
Sorry. Hey, shush. The star is 360 light years from us. Mm-hmm. The planet is 110 astronomical units from its star.
So give us some perspective then. I mean, we know 1 AU is the distance from the
1 AU
Earth
is
to the sun.
The sun to the Earth.
Right. Pluto is like
80-ish.
Yeah.
40.
And so
40. Yeah.
Yes.
40-ish.
40
wow, I really do need to give you my PhD. I'm bad at numbers. Wow.
Right. Yeah. Oh, it all just falls out of your head. So we're looking at
at something.
Yeah, almost triple the distance from the Earth from the sun to Pluto.
Yes, we're all doing fantastic with numbers right now.
Yeah, we'll be all right.
Moving on past that, the planet itself is a little bit bigger than Jupiter. The star is about the size of the sun. The planet's a little bit bigger than Jupiter, and yet this planet is so far away from not only from its star, but from the place in the a solar mass star's solar system where we think that Jupiter-sized planets should be able to form, where we typically see them, where we expect to see them, where we have seen planets this age before, and this one is so much further away. So how did it get there?
Yeah.
Is the open question. We don't have an answer to it yet. There's a couple of options. So to make a planet that size, you can either use one of two pathways. The first is you can basically build it up from smaller bits, called core. So that's a method called core accretion. You take a bunch of smaller protoplanets, dust and gas, and it all gloms together and you get a Jupiter-sized planet after a while. This planet probably couldn't form that way because in order to make a planet, you first need to have the material. And so when the star and the system was forming, all of that material was much closer to the star than where this planet currently is. So it can't have formed at that spot by core accretion. It could also have formed basically from the top down, like a star would, but from the collapse of a large gaseous cloud. and it would collapse down to form a planet.
I mean, you
We
could
think that this is
definitely
like
have
how-
a binary star system with
That's
that
how
kind of a
binary
separation.
star systems form.
Right.
This is how we think brown dwarfs form as well. The problem with that method, though, is that with core collapse, direct collapse, it usually makes things that are much bigger than this planet. It's usually hard to stop getting material when
Right.
you do direct collapse, and this planet is too small to have done that.
So like the material
this
should have
location.
gone into the star, not into this region and become a planet.
Right.
Right.
So neither way of making a planet seems to work for this planet at this location, which leaves hidden option number 3, which is that it didn't form in this location, but instead formed closer into the star and migrated outwards, was like knocked away, which is something we think can happen. We've seen evidence that it has happened elsewhere, or even in our own solar system, as planetary systems they're forming, they're settling down, things are very chaotic, and some other planets, some stars, some whatever, can gravitationally knock something out of orbit or into a different orbit.
But doesn't that almost exactly match the description of Planet 9? That you've got a Jupiter-ish mass planet way out into the Kuiper belt that is influencing, whether or not Planet 9 actually exists or not. Like if there is this mysterious object in our own solar system, like that's what it would look like if you saw it from afar, wouldn't it?
Kind of maybe, though I think we think Planet X,
Neptune.
Planet 9, whatever we're calling it now, is a bit smaller than this planet.
Yeah.
But yeah, similar idea, where there was some gravitational interaction that knocked a planet out way further from where it actually formed. The problem with this particular planet we just found, though, is that where's that other object? Where's the thing that knocked it out of orbit? There's nothing else showing up in the images that were used to detect this planet. So we don't know. The answer is going to come from more follow-up observations of this system. Maybe it's hiding, maybe this other object, whatever it was, is too close to the star to capture with direct imaging, which means that maybe we'll have to follow it up with some other detection method like radial velocity or with transits, something like that, but that will require more telescope time. What's it doing there? We don't know.
I'm pretty fascinated by this idea of rogue planets that, like I know Scott Gowdy and co-investigators sort of did a paper about the number of rogue planets that could be moving around the Milky Way through gravitational microlensing. And it looks like there's a lot of them. And so this could be an example of one of these objects that happened to form close enough that it was illuminated by a star that we could see it. But there may be many more of these things out there. And I guess the question is, can it survive without feeding that dust over to the star, without the star gobbling it up? And maybe we'll be able to set some kind of limits.
See.
I mean, if we see more of these things and see no other, like it is a binary system in a kind of a weird way.
Yeah, and the more direct observations we get of this particular system, the better we'll understand the dynamics and the orbital orbital configuration and motions of this planet. We only have two observations a year apart, and the more we fill in that orbital trajectory, the better we'll understand what this planet's possible fate might be.
Right. Very cool. All right, so I'm going to take a question from the audience because I liked it, and I get to do that. So Hal McKinney asks, how do science writers like yourselves make sure that some critically important astronomical event doesn't escape your immediate attention like in the middle of the night? Moya, how do you do that?
I don't think I do that very well. I miss a lot of stuff, but to minimize the amount of stuff that I miss, I follow science writers on Twitter. Check up on them every once in a while.
Yeah. Dave? Sure, Kimberly, go ahead.
Oh, I was going to say, I also follow lots of scientists, science writers, all the agencies on Twitter. I also get a boatload of email alerts and newsletters and announcements in my inbox every day. and I make sure to go through them. And if it's in the middle of the night, I should set an alarm.
Yeah. Dave, what about you?
Well, for observational astronomy, like new comets and meteor showers, and there's some key things I'm hitting every day, like the Minor Planet Center. I'm looking at like if there's any new comets discovered. That's usually my first check in the morning, and then I'm looking at NASA JPL to see what their orbits might be, if there's anything interesting. In Twitter, I get a lot of my key alerts, like people are saying that they saw like a fireball over in Europe or something like that, or they're seeing meteor activity, or comet is brightening, or things like that. And like Kimberly says, there's a lot of newsletters and aggregate feeds that are going to me that will be pushing that out. Honestly, like there's so much space news out there nowadays that as far as space flight news and stuff, I just have to let some of them go.
Yeah.
It's like you can't write about all the things all the time.
And you do have somebody generating a handy list for you every day that you could look through and pick stories from, should you wish.
Yes. Yes.
One of the other things I've learned about with Twitter, which I didn't actually think of until I traveled over to Iceland for a science conference. But a lot of the things you see on your Twitter feed or in like the trending topics and other news items that you get, it's all very location specific to where you are right there. And so if you want to know about a comet that may be over Africa or
go to Africa.
China or somewhere, it's not going to show you that unless you tell it to not give you location specific news.
Oh, interesting.
Broaden your Twitter.
Yeah.
And it will, and like interact with those stories, and the algorithm will pick it up, and you'll get more news from around the world.
That's interesting.
The morning the Chelyabinsk meteor came out, I was getting like slammed with videos from everybody like saying, "What is this thing?"
I was getting phone calls. So yes. that's how I got on that story.
It was early AM for the East Coast, so that's when we heard about it.
Yeah, I think it was like 3 a.m. or something, and I was getting phone calls. My philosophy on this is that I practice what I call slow news, which is that I think that trying to stay on top of like all of the fast breaking news stories is kind of exhausting on your writing team, and I would rather us be a little slower, a little more contemplative, and come out a couple of days later with Universe Today. And so it's a very, Dave, I hope can attest to this, that it's a very kind of laid back, lackadaisical. Yeah. There's no, quick, get on this story. Like, because I think it just grinds up your writers and spits them out in the end. And I would way rather people just have fun with their jobs. And if we're not first, I don't care. So that's my approach is to just go slow and just work on stuff as we want to at the pace that we want to. And if we miss stories and we're not first, I don't care.
You got to let some go.
And you know what? Scientists actually prefer that sort of thing. They like having a little bit of time between what happened and like when the data's coming out, and they actually like having some time to think. Scientists, who knew? They like to think and like analyze, and it actually can help you provide a lot better context for what actually happened and sort of the scope of a story.
There is a tug of war too, like say when New Horizons went by Pluto, it's like I wanted to write about it, of course, and I did, but I also want to just sit back and watch because it's really cool. So it's, there is that tug of war too. It's
there's definitely
I like to be a spectator too.
Yeah, a bunch of times when I do that too, I'm like, I'm not going to report on this. I'm just going to watch it and just enjoy it and think about it and then move on to something else. But yeah, I think that it is a race to the bottom for news, and if you're trying to get faster and faster, get closer and closer to the second for when these stories are breaking, the price you pay is just in sort of human like exhaustion, and it's not sustainable. And so you just got to pick your battles as you're doing this communication, and some stuff you got to let these fish, and because you will go crazy. Like you'll see everything. You always sort of compare yourself to the work that everybody is doing simultaneously. You watch on Twitter and you're like, oh, Moya got this story. Oh, Kimberly did a great story over on EOS. Oh, Dave Dickinson, why are you writing for astronomy or Sky Telescope?
That about me?
Yeah. You had a great story today that I saw.
I did. I love that story. It was great.
So you'll go crazy, and you have to just recognize it. You just And the other thing I really like to do is pick stories that aren't breaking, that are just really interesting stories that nobody's working on, and you have all the time in the world to find them, work on them, interview the researchers, report, move on. So
I will pick things where I'm like, I've never heard of that. I'd like to know. I'd like to fill my brain with that myself. So, I want to go down the rabbit hole. So,
yeah. And so, my recommendation really for anybody who is going to try to go into like journalism in general is you just have to try to avoid the breaking news as much as you can, because it'll grind you up and you can't sustain it for very long. So better to specialize, write long pieces, other mediums, and just get better at your craft. Okay. Moya Mcteer, what have you got for us?
I have this really cool story about baking meteorites, and I saw it and I thought it was so cute. So researchers at UC Santa Cruz, they took samples from 3 different meteorites and they put them in an oven to see how they could better understand the way that atmospheres form around young planets. So they took these 3 different meteorites that are, I guess, pretty well studied. One that was discovered in Australia in 1969, one in Western Sahara in 2013, and one in Costa Rica in 2019, 3 different meteorites. They took them and tiny little samples from them and put those samples in an oven or in a furnace, and over time ratcheted up the temperature, going from 200 degrees Celsius up to 1200 degrees Celsius, which, as far as I can tell, is as hot as the machine could get, although that is not as hot as planets can get when they are forming. So this is at the lower end of the temperature spectrum for planet formation. They increase the temperature by a few degrees every minute. All of these meteorites that they were using were carbonaceous chondrite meteorites, which is a special classification of meteorite that only account for about 4% of all of the fallen meteorites that we have collected. So it's, I guess, a relatively rare type of meteorite, but they're really cool because they are the oldest and least heated objects in the solar system, or some of the oldest and least heated objects. So they actually represent material that formed the sun and solar system. So by studying these meteorites, you can learn more about the composition and makeup of different objects from the early solar system.
Go ahead.
No, I mean,
well, I was just going to say, like from understand, right? They got samples of atmospheres of objects early on in the formation of the solar system, which is kind of crazy.
Yeah. The idea behind this project was that they wanted to take rock samples that represented, what maybe the Earth could have looked like early on in the solar system, or other rocky bodies in the solar system, and they heated them up to model the way that these rocks get heated up in the planet formation process. Like Kimberly was saying, 14 million years after a stellar system is formed, these planets are still really young and really hot because of all of the heat that you get from the friction and the collisions when these planetesimals are forming. So they put these samples in an oven, in a furnace that was connected to a vacuum, so they could create a vacuum inside, and a mass spectrometer, which separates molecules by their mass so that you can figure out what these samples are actually made of. And they measured that the material, the gas coming off of these heated rocks, was mostly water vapor. It was about 2/3 water vapor, 18% carbon monoxide, 15% carbon dioxide, and then a little bit of hydrogen and hydrogen sulfide. And that was pretty stable across all of the different all 3 samples that they used. So each of these samples they had similar composition, and they also produced similar gases.
So did they come from the same object?
No, they came from different objects. They were different meteorites. They fell on Earth in different places at different times. But across the 3 of them, they were made of similar materials because they're from the same solar system. So they, formed from the same mixture of dust and gas and molecules that everything else in our solar system formed from.
Right. And so that water vapor, carbon dioxide, was that a primordial atmosphere of planetesimals in the solar system?
We think, yeah. So that was the point of this experiment, was to see if it could give the researchers any type of expectation for what a young planet's atmosphere might look like after the planet gets heated up, which causes the gas to come out from the inside of this planet. So this would give us something to compare observed data to in the future, maybe with James Webb, when we can study the atmospheres of these planets.
With that much water coming out of these samples, I wonder if that helps explain the source of the Earth's water. I mean, if you've just got that much water out of meteorite rocks, like clearly they're infused with water, and so it makes a far simpler explanation is that the water was in the rocks all along. Right. So.
Yeah, the water was in the rocks, and more rocks continued to fall on these planets that carried water with them.
Yeah. That's very cool. Dave, do you want to talk briefly about the upcoming Crew 2 flight?
Yes, Crew 2, SpaceX's Crew 2 Dragon mission is carrying 4 astronauts to the International Space Station. Originally, they were launching tomorrow morning, and now they're launching Friday, which actually is pretty good for launch viewers because this is going about half an hour prior to sunrise. So if you're on the U.S. southeast coast, this is going to come right up the East Coast. We checked on the launch geometry on this. This should be highly visible up the East Coast as it's coming up. So I'm going to be on the rooftop with all cameras running, of course. So this ought to be a very interesting one to see. The launch is at 5:49 a.m. Friday morning, Eastern time. And they're docking Saturday. So assuming they go, it's interesting. They have to have the launch track clear all the way up weather-wise. The reason being, if they have to abort, and if the Air Force, or rather Space Force now, pararescue have to go and actually pick them out of the water, they don't want them to abort into a storm or something like that. So that makes the weather prediction for this kind of launch. It not only has to be clear at the Kennedy Space Center launch site, but has to be clear all the way up the Atlantic seaboard. Friday, when I was looking at it, the weather looks pretty good. If not, the next window is probably Sunday, and that's going to bump them back because they have to launch to chase after the International Space Station.
Right.
So the earlier they go, if they launch in darkness, we won't see them come up the coast. We had a Starlink launch do this last month, as a matter of fact, and it looked, I don't know if you can see this, it looked like this from Norfolk. So it was highly visible from here. So it was one of the more, yes, and you can see Cape launches from, I'm in Virginia, Norfolk. So you can see if they launch just right at sunrise or sunset in the twilight, and they come up the East Coast, and usually they have to go after the International Space Station as well. But some of the Starlinks have been doing that too. So it is proof that you can see them that we're several hundred miles north. So I would be out there Friday morning if you can. If you're like anywhere from Maryland down to Florida, say, it would be a good place to watch this come up.
So I should set my alarm, is what you're saying.
Yeah, that's true. You're right up in DC. You should see it.
I am.
Yeah, should be able to see it.
Yeah.
All right, and then a couple of other quick announcements. It looks like SpaceX's SN-15 is going to attempt to flight sometime this week, probably near the end of the week. There was a couple of road closures that happened, I think, today and tomorrow, but it looks like they were based on them moving some stuff in and out of the launch site. So hopefully we'll see this thing launch by the end of the week. And not explode. So here's hoping. The big news that came on last Friday, which caught us all by surprise, and it turns out it looks like there was a leak that sort of made NASA quickly do a press conference. Because, I mean, who does a press conference at 4 p.m. on Friday afternoon? I mean, half journalists are at the bar at that point. So, and so NASA has announced that they've chosen SpaceX as the provider for the lunar landing program, the human lander system. And so they're going to fly astronauts on the Space Launch System in the Orion capsule out to lunar orbit. There they're going to meet with a Starship that's going to be orbiting around the moon. They'll get into the Starship, and get lost inside the Starship. Then descend down to the lunar surface, then hop around the moon, do their moon exploration stuff, and then launch back off the surface again, dock with the Orion, or it'll just disgorge the Orion, I'm not sure, and then they'll return back home from that vehicle. And it was a big surprise, but it turns out that the other providers that were there were just way too expensive. That SpaceX provided such an inexpensive option that they ended up having to go with this choice, and the capacity of the Space Launch System of the Starship, the capacity of the Starship should give them a lot of room to grow in the future as they add more components and more equipment for future moon landings. So it was a big surprise. No one was anticipating something like this. It was they'd given money to a bunch of different providers, but this definitely is an interesting development, and I think it shows that, and also, NASA is now partnering with SpaceX more formally on the Starship. They're going to be helping provide expertise both in orbital refueling as well as launch, with just some of their engineering expertise to help get this thing flying and doing what it's supposed to do. So hopefully this is a really good step in the next stage. We will see. Yeah, and people are saying in the chat, and a new NASA administrator. Like, it's been a crazy week. It has been a very big week for space news. So, so that's it. That's all I got to say about that. All right. Well, we're going to move to the interview portion. So I'm going to let my co-host go. Dr. Moya Mcteer, what are you working on now, and where can people find out more?
I'm now working on my podcast called Exolore. Season 2 comes out tomorrow. So if you're interested, you can head on over to exolorepod.com or wherever you get your podcasts. And you can find me on Twitter at GoAstroMo.
Awesome. Kimberly.
Yeah, well, as you said, I just published a really fun article about what a metal volcano would look like. And
like, yes, someone made one,
yes, this is a space story because we're going to a metal asteroid that may have once had volcanism. So what would a metal volcano look like on asteroid Psyche? You should read my article on eos.org to find out.
Yeah. I mean, the researcher that you talked to actually simulated, that science experiment.
Not just simulated. She went to, I'm going to a little explanation. She went to the Syracuse Lava Project and melted down a bunch of basalt and metal and poured it out. Like she made lava.
Yeah.
In this giant crucible, in this giant furnace, and poured it out to see what a metal volcano would look like. Yeah. There's awesome videos. Check it out on eos.org and on Twitter at AstroKimCartier.
It's like that.
That was a smooth transition.
It's like that baking soda, vinegar.
Like that,
right?
But much bigger. Except and with actual lava.
With metal and basalt rock. Yeah, exactly.
Right.
So cool. All right. And if people want to find out more about you, where do they go?
Oh, I already did that.
Oh, did you?
It was a very, very smooth transition in there. You may have missed it. You can find me on Twitter at AstroKimCartier, and all my stuff is on eos.org.
Awesome. All right. Dave Dickinson.
I am at AstroGuys with a Z on Twitter, frequent contributor to Universe Today, Sky and Telescope, Astro Gear today, and I am going to be on the roof Friday with all cameras running, of course, for the Crew Dragon launch.
Awesome. All right. So I've got an interview on Friday morning with someone from the James Webb Space Telescope science team. He was on the committee to figure out which things James Webb is going to be looking at, which was recently closed and announced. So we'll be just going over every interesting science project that's been proposed for James Webb to give a sense of the capabilities. But lots of other great interviews this week. So if you want to go back through my channel, I've got lots of great stuff, including Michio Kaku, Avi Loeb, and then a whole bunch of other people as well. So it's been a busy week. Okay. Well, I'm going to put you guys all back on the screen, and then I'm going to say goodbye, and then we're going to move on to the interview portion of this episode. So thanks, everybody.
Thanks, Fraser. Bye.
See you guys later.
Thanks, later.
All right, back to me. Let me find my interview. All right, let's see if this works. Here we go. Oh, okay. All right. Here we go. All right, our guest today, Dr. Amanda Hendrix from the Planetary Science Institute. Welcome back to the Weekly Space Hangout.
Hi, thanks for having me.
I think it's been a couple of years since we talked to you last. So what are you working on?
Oh gosh. I am busy working on a few things, continuing work on LRO LAMP, because that mission is going strong and we're continuing to get great data of the moon and thinking about water on the moon. And I am also continuing to work on Cassini UVIS data, so ultraviolet data from Cassini, because even though that mission has ended, there's tons of data to go through and lots of interesting projects there. And I'm also thinking about asteroids. And
well, so the through line that really connects your work is this idea of using ultraviolet to observe the solar system. So can you explain why ultraviolet is a useful wavelength for the solar system? What does it show us?
Well, okay, that's a great question. So ultraviolet wavelengths, I think, are really useful for a variety of reasons. So traditionally, they've been used, for many decades to look at atmospheres. And so, and atmospheres and aurora, and people would use, like, for instance, the International Ultraviolet Explorer, IUE, back in the 70s and 80s to look at Jupiter and Saturn, atmospheres and aurora. And even early observations from like Mariner 6, Mariner 7, Mariner 9, UV instruments there looked at Mars's upper atmosphere. And then what we started doing a little bit more with IUE and with HST and also starting with Galileo is thinking more about using ultraviolet wavelengths for looking at surfaces. So like Earth's moon, looking at, there's not much atmosphere to have to look through there. So we could just look right at the surface. And also looking at icy moons. So Jupiter's icy moons, when we got there with Cassini, we could look at Saturn's icy moons, and also using space telescope data to look at asteroids. And there's a lot of things that you could do, like you could look at surface composition, space weathering products, and really interestingly, what we showed with Cassini is that you can look for geologic activity, like look for plumes on Enceladus.
Well, so I want to take those bit by bit. So, like, how does looking at, say, the moon or an asteroid in ultraviolet show you evidence of, say, weathering or?
Sure.
Yeah.
Okay. So I want to talk about what for the moon, especially weathering and water, because you're probably familiar that the moon's water has been detected using infrared wavelengths also.
Yeah, that's like the other side of the spectrum.
Exactly. And so this is a kind of a nice A, confirmation, and B, kind of another way to look at water that has, because every set of observations that you use has its own set of uncertainties, right? Complications that go along with it, and tricky things that you have to think about. And so in the infrared, when you think about looking at water on the moon, you have to be concerned about thermal emission and making sure that when you're looking out at those longer, 3 to 4 micron region, that you correct appropriately for thermal emission that you get there. In the UV, you don't have that problem. And so maybe that's a nice way of comparing results. In the UV, one of the issues that we have to work with is there's not that much solar flux to deal with, because the solar continuum really drops off down into the UV. And that's what we're looking at in all of these observations, is reflected solar flux.
Right.
So usually with the UV, we have to maybe do longer exposures, longer integrations to build up enough signal to do the observations.
But will, like I know that, say, bees, for example, have the ability to see into the ultraviolet, and that helps because certain kinds of, I guess, flowers reflect the sun's ultraviolet rays in a different way. So, I mean, is there an advantage with looking at the ultraviolet? Does it reveal features in a way that makes them pop that you wouldn't necessarily see in, say, visible light or infrared?
Yes, that's a really great point. Not only is there a very strong water absorption in the UV, there's also diagnostic spectral features that are due to carbons in the UV. And if you think about it, you know that there's there's got to be tons of carbon in the solar system. It's such a common element. And yet it's really hard to say exactly what state it's in and how much it's in, say, when you look at an asteroid. And that's because when you look at it, you say, okay, well, it's pretty dark. It's low albedo. It's probably carbonaceous. And we know that, when we have when we look at meteorites, we know that they have carbon in them. And so the asteroids probably have carbon in them too, some types of asteroids. But there's no spectral features when you look in the visible or in the infrared of carbon. And even carbonaceous compounds to a certain extent. But then when you look in the UV, you do actually get, these spectral features that are quite diagnostic of the type of carbon. And also what's really interesting to me is how much processing the carbon has gone through. And so that kind of tells us something about maybe the relative age of the surface, maybe even where in the solar system it formed and how long it's been there. Because the longer you can imagine a surface has been in a particular place and has been getting pounded by UV from the sun, pounded by micrometeoroids, pounded by solar wind, then the carbon on the surface evolves and it basically becomes more and more carbonized. So, organics that might be on the surface degrade and become amorphous carbon with exposure, and they might even become graphite. Wow. And so these are the spectral features of these amorphous carbon and graphitized carbon that we can see in the UV that you can't see in other spectral regions.
That's really interesting. And so by being able to look at these kinds of spectral features, you're seeing, this is older. This is an older surface, sort of the way that they do crater counting to be able to sort of see. Yeah. But in this case, you can actually just look at the features of the surface and go, okay, the carbon, how rough is the carbon, or even how much of it has turned to graphite to tell you how old it's been. Now you mentioned briefly that this is going to be great for searching some of the icy worlds, some of the water worlds in the solar system. So how does UV play a role in that?
Right. So out in the outer solar system, where we know that a lot of these moons are ocean worlds, or are likely ocean worlds with subsurface oceans underneath their icy shells. What we can do in the UV, again, because there's these diagnostic spectral features that tell us how much of different vapors are there, different gases. Like, for instance, with Cassini, we use the UV instrument to look at how much water vapor is in the Enceladus plume. Mm-hmm. And so it turns out that it's quite a sensitive technique for finding water in gas form. Going back to the original uses of UV observations, looking at atmospheres, thin atmospheres. What we first did with Cassini UVIS at Enceladus was to look and see, does it have an atmosphere? And we did what's called a stellar occultation, where we would look at a star, watch it pass behind the disk of the body, and does that stellar signal get absorbed at all by any gas atmosphere that's around the body? And we found, it doesn't. Except at the South Pole, there must be some sort of gas there. Yeah. And so that's kind of a sensitive technique that we can use to look for atmospheres, thin atmospheres, and geologic activity, especially in the form of plume activity.
And sort of the terrible irony is that it's really looking like the vast majority of the liquid water in the solar system is in these icy moons, possibly in places like Pluto, some of the dwarf planets. Like, it's everywhere, and yet it's all covered under this thick sheet of ice that makes exploring it difficult, nigh impossible. Yes. But you get these situations where it is making its way to the surface. And so it feels to me like we can put those two ideas together. You've got your ability to seek out carbon in its different forms matched with your ability to sort of look into the plumes of water. So are you able to sort of bring it together to maybe sort of sense the environments under these icy moons?
Well, yes, I think we can. Because, in addition, for instance, at Enceladus, we know that there's mainly water particles, water vapor in the plume. And that makes its way out into the Saturn system. It also, some of it makes its way back onto the surface of Enceladus. And so we can see signatures of the organics, first of all, in the E-ring, which is, that big, broad, diffuse ring of material that is formed by Enceladus, but all of the moons, or all of the inner moons anyway, of Saturn orbit Saturn within this E-ring. And so they get coated by the E-ring.
Right.
And so we can see on those surfaces evidence of the organics that are in the E-ring, that are sourced from Enceladus's ocean, because we can see their spectral signature, and especially we can see kind of their aging. We can see them because what happens is the organics, as they get exposed to different weathering processes, they first kind of tend to get reddish. And then as they get more and more exposed, they'll get darker and redder and then kind of end up turning black. And so this is a good explanation for why we see some subtle albedo and color variations on the surfaces of these icy moons at Saturn, is because they're getting exposed to some of the organics from Enceladus's ocean, and that ends up kind of coloring them.
That's amazing that we can actually see I think, when you sort of take this puzzle apart, the fact that, the E-ring is figured out that that's the source coming from Enceladus, and the fact that Enceladus is spraying out its oceans into space, and that the oceans are containing these various carbon compounds in them, and that now that explains the coloration on the moons going around Saturn, and is in fact a diagnostic tool to help you see what's going on inside Enceladus. It's such a phenomenal sort of connecting the dots. I love it.
It's really neat. And it makes me think about how interesting the whole Saturn system is, and how interconnected everything is. At Jupiter, you've got a different situation with Io spewing out all of its kind of sulfurous volcanic stuff and doing some amount of colorizing of the other moons also there. But also then you have a different situation there, because there's also a lot of charged particles from Jupiter's environment, less so in Saturn's magnetospheric environment there. So I don't know, lots of different sort of interesting exogenic processes going on.
Well, the thing that I sort of find that's really interesting is how everything is connected, that you're starting to see, when before you just be like, well, it's, this planet looks different from that planet, this moon looks different from that moon, but then it's starting to see that in fact all of the objects in the solar system have been influencing each other in various ways through micrometeor. You can imagine this story that some large asteroid formed after the solar system was smashed into tiny pieces. The tiny pieces, were in a cloud and came down as a micrometeorite shower on some other object and is coloring it. You can tell the age and so on. That the more we learn about these processes, the more we can sort of unwind the history of the solar system to go back to literally the formation.
Right. And it's really interesting. And also the idea that you were mentioning earlier of kind of putting together the geology with the colors and chemistry and spectroscopy of the surface, like the cratering. You can understand a relative age of the surface by looking at cratering, but put it together with the spectroscopy and the chemistry, and you really have got a powerful story. And you could use that tool anywhere in the solar system.
There's like a noise going on in the background. Do you hear that on your side, or?
Yes, there's a beeping.
Yeah, okay. Is it coming from your computer? Is it coming from...
You want me to... I have to go turn it off.
Oh, okay. Yeah, it's definitely...
Sorry, hang on just a quick second.
Got it?
Sorry.
No problem. Yeah, maybe I'll cut that out. Okay. Or maybe I'll leave it in. It was pretty quick. Cool. So we've got a few minutes left. I just want to talk about the TREX program that you're involved in. What is that?
TREX is the toolbox for research and exploration. And this is what it is a node of the NASA Solar System Exploration Research Virtual Institute, which is SSERVI. So what it is it's a virtual team of about 33, 35 scientists across the world, really, but mainly in the US. And what we are focusing on is using research and in different ways. So we're doing modeling, lab data, analysis of spacecraft data, putting it all together so that we can prepare for further exploration, especially of the moon, but also of asteroids, and even preparing for humans going to the moon. And so what we're doing is we're looking at a lot of lab data, and we're doing some kind of cutting edge lab data where we're looking from the UV all the way out through the mid-IR, looking at planetary conditions, so at the proper temperature and pressures, at different minerals and different mineral mixtures, and also meteorites, and we'll be looking at lunar samples too. And the really new thing that we're doing is looking at very fine grains. So sub 10 microns usually. And this is because we know that a lot of these surfaces, and especially the moon, but even asteroids, are covered because of space weathering processes, a very fine grained regolith. Now there's a range of grain sizes, but it does go down to very, very fine grains, which have not been well studied in the lab. In particular, their spectroscopic characteristics, which the grain size can really affect the spectroscopic signatures of these minerals. So what we're doing is we're taking the lab data very carefully and at multiple labs so we can really do a lot of cross correlations, cross calibrations. And then what we're going to be doing is comparing them to existing lab data, like from LRO and other lunar missions and other space missions that have looked at asteroids, to put together what grain sizes are on these bodies. And in particular, how do they link to potential resources like water?
Right.
We know there's water on the moon. How does that link to grain size? And can we use that as a tool for when future robotic missions go to the moon, when future human missions go to the moon? They're going to want to get at some of these resources, and how can we help? By looking at different grain sizes and where the water might be present on the surface.
Yeah, so to know, okay, if we go to this spot, we're more likely to find the kinds of resources that we require that we can use for our in situ tools.
Exactly.
Yeah.
And it's all about kind of risk reduction, really. We want to help out future missions to know exactly where to go, how much water might be there, how much other resources potentially might be there, to help reduce risks to those future missions, because it's more of a sure thing about what they're going to find when they get there.
Very cool. So if people want to follow your work, find out more, where should they go?
Okay, so we've got trex.psi.edu. That's our webpage where you can learn all about TREX and what we're working on. And also, I have a webpage at psi.edu. You have to look for Amanda Hendrix.
Yep.
And I update that from time to time with different things that I've been working on. So
perfect. Well, Dr. Hendrix, thank you so much for taking the time to chat with us today, and good luck with your research and saving everybody time when they land on the moon.
Thank you so much. It was fun to talk to you.
Take care.